Hello everyone. So I'm Kaustubh Dhole, and today I'll try to cover some topics which are recent to NLP, natural language processing. What's basically happened from 2010 to 2020, the most important problems, and a few problems of 2021. So uh, I I started my I did my engineering in BITS Pilani. And I was working for machine learning applications for biology first, where I got interested into machine learning, and then I I was there for a year and a half at TIFR, where I worked on operations research and a bit on queuing theory specifically. And after that, for the last 6 years, I've been working in a company called Amelia, or it's the original company's name was IPsoft, so now they've been segregated. So there, basically, I work on natural language processing, where we attempt to design a conversational system, an ideal conversational system called Amelia. And my work involves basically two things, like that is R&D and engineering. So in terms of R&D, the main topics that we deal with is it's heavily oriented for natural language processing. That's on Python frameworks. We code a lot of in Python and Java, and we do a bit of work in speech also. And there is a bit of work in effective computing also. So effective computing involves mainly trying to understand effects, or basically personalities, mood, emotions. So like emotion is a short-term effect, mood is a medium-term effect, and personality is a long-term effect. So how do these change during the course of a conversation? So how do these change for a bot as well as for a user? So we try to model those. So today I'm going to speak specifically about the first part, that is NLP. I'll just go through the rest once. The other part of engineering, basically our whole stack is basically in Java. That is our whole framework. Amelia is totally written in Java, and there are other code bases in which all our experimentation takes place in Python. And our speech modules, where speed is very much required, is basically in C++, and some bits and pieces of code in Go also. And there are teams which work on front end also, which work on React JS and Angular JS. And besides this, there is obviously other teams who work on animation, of developing the avatar of the conversation system. So Amelia is deployed as a woman, like as a woman robot. So making the animation features, how it should respond, like visually, how a lip should move, how a eye should move, etc., and how that synchronizes with speech. So that is one aspect which a team also delves into. And finally, after besides R&D and engineering, there's obviously a little philosophy needed, that how humans interact with each other, and how we can take aspects of those interaction and try to model them uh, in uh, in a bot, or let's say in a conversation system. So basically understanding how humans understand language. So while that is not a very solved topic, we can definitely try to attempt or try to make some guesses for that. So yeah, so basically NLP in general can be roughly divided into natural language generation and natural language understanding. So specifically in terms of natural language understanding, we have a couple of problems in which people the aim is that we develop systems which try to understand a sentence, a paragraph, a document, etc., of the user. So that has different levels of understanding. So, for example, understanding how words are constructed, that study is called morphology. So there's a lot of recent work which is done on tokenization. That is how we could tokenize words and segment them. So recent literature has basically shown that you don't need to tokenize like sentences in terms of words, but in terms of subwords, because that helps in let's say out of vocabulary handling out of vocabulary uh, problems also. So for example, today we are today the president changes, India's president changes, or India's prime minister changes, and we have a new prime minister, then the words that now all the documents which are there, they have been, let's say, trained, all the model systems have been trained to use old words or our old prime minister or old president. As soon as it's changed, so our model will suffer. So we need to ensure that we handle out of vocab words also, as well as our systems remain constant throughout time. So subword tokenization says that instead of breaking a sentence into individual words, you break a sentence into individual subwords. That means that even if you come up with a new word tomorrow, then you can break that word into smaller subwords, and your system would be basically trained on these subwords rather than those words, uh, the novel words. So any novel word could be broken down. Then, in natural language understanding, specifically, one of the most famous problems is syntactic parsing. And syntactic parsing involves creating two types of trees, that is, dependency trees or constituency trees. And there's a whole lot of theoretical literature on that. But what's the best way to create trees? And a lot of deep learning is currently used for constructing these trees. How do these trees help is basically these trees create a agnostic representation, so you can change sentences, you can have different words in the sentences, but your tree will kind of remain the same. That means that if I say VIT has organized a conference, or let's say, or if I change the sentence to the government of India has organized a conference, the tree structure for both will remain the same. So this helps. So you can, if you decide to write rules, you can write rules over the dependency tree or over the constituency tree, and they will apply to whenever you have different words. So that is specifically on designing trees. So that's a very say not an age-old problem, but it's a very famous problem. In fact, there's this recent project of universal dependency trees, and that recent project tries to create a universal representation of dependency trees. That means one representation for all languages. So as close as possible a representation, so that systems which work or which are dependent on one dependency tree, like, or rather one language, they can be easily shifted to another language as well. And an interesting thing about universal dependency trees is that the representation that so basically a lot of scientists from different universities came together and said that, okay, like, instead of creating different dependency trees or having this different formats of these dependency trees, what we're going to do is we are going to have one common format, and which is our universal dependency trees. So this common format, it turned out it's very similar. In fact, Indian grammarian, who's the father of Indian linguistics, called Panini. So he had developed a system in which, for specifically for Sanskrit, for developing a sort of a tree representation. And universal dependency trees are very consistent with that representation. So that is one interesting part. Uh, the other part is discourse analysis. So discourse analysis is understanding things at the sentence level. So let's say, I mean, for morphology, you understood how words are constructed, how words uh, like bring the meaning that they have. The next is discourse is at the sentence or at multi-sentence level. So when you have a dialogue going on, when you have a conversation between two systems at that point of time, how does meaning develop? So that is what discourse is. Or to be specific, um, what are good representations of a sentence? So that is what it is. So mainly NLP, if you look at that way, NLP deals with words, then at the phrase level, then at the sentence level, which is your discourse analysis. And then there are other parts of NLU also, which are like semantic role labeling. So semantic role labeling is also a very important problem, in the sense that it identifies within a sentence, it aims to identify who did what to whom, when and where. So on the right, you can see there's a sentence here: New Mexico was won by Obama. by a margin of 5% in 2008. So specifically, New Mexico is the thing that was won, and Obama is the person who won. So Obama is the agent in the terms of semantic role labeling, or in the so semantic role labeling assigns. So these are basically semantic roles. So here, patient is a semantic role, agent, extent, temporal. So once these constructs are identified within a sentence, then these can be used for other tasks, basically, like can be for deciding what a bot should do, or maybe when a bot should do something. So for example, the temporal, which tells us, okay, that this part, that in 2008, is basically a temporal role. So that temporal role can help us tell, like, okay, that something has happened in 2008 rather than 2007. Or maybe if you want to extract out time oriented or date oriented things, we'll do that via the temporal tag. So SRL is basically trying to identify these individual constructs, which tell us when did what each person or what each unit is doing in and around an action. So here the action is winning. So what's happening with these units around it? Then there are aspects. So these are all of the ones which were general NLP aspects, in which they did not depend on any domain. That is, pretty much they would remain constant across domains, arguably. So the other part is conversational AI, in which there is it has its own natural language understanding. For example, detecting user intentions or user intents and their entities. So for a sentence like book a flight from London to New Delhi for tomorrow, there are tasks in which you want to identify, okay, that this sentence represents booking of a flight. And you could specify that in very different ways. Like, I want to book, let's say, I want to book on this website for a flight to go from London and then reach Delhi by tomorrow. So there can be multiple ways, and you would want to identify the most important elements that are there and the crux of the user. So here, the crux of the user or the intent of the user is booking, and the entities, the specific entities which the user wants to is talking about is London, New Delhi, and tomorrow, like a time. So how these are used later in a conversation system is, once these are extracted, these can be used in any automated system. So this is kind of converting a natural language, a very noisy natural language, into a more structured form, which computers can consume. So basically, when you identify this structured form from this unstructured language, you could basically execute tasks. So that is specifically intents and entities. And then there are NLU also involves understanding high level cognition tasks. So when I mean high level cognition, those which are not necessarily um, easily understood, and you could say sometimes even as humans we fail to understand them. So like humor, figure of speech, so sarcasm, etc. So all these are basically they not only require us to, for example, understand like the surface form of the sentence or the direct sentence, but it can have a meaning which is very different from the surface form. So for example, if we say that the sun is drowning, and that definitely does not mean that the sun is actually going inside or like moving into water, right? So that it has a metaphorical usage, and it represents that the um, sun is sun is setting. So that's the thing. So humans are very good at it, but making computers understand that is requires either a lot of training data, or it requires skills like reasoning, which I'll discuss further. So this is overall in terms of what NLU has. The other part of NLP, the most another interesting aspect of NLP basically is NLG, or natural language generation. So this has, I mean, you can just imagine, like, from generation, what all could you generate. So basically any sequence of text, whether it be summarizing a news article, or translating one language, one piece of text from one language to another, or generating a question from a fact, or having conversation in a dialogue by generating the next response. So there are a plethora of tasks here. So most of the tasks, if some of us are aware, so the last decade was very much focused on LSTMs. So that is, and once LSTMs, after LSTMs, then transformers have been in the last 3 years shown very impressive results. So most of all these tasks that you see on screen have got their state of the art from the transformer architecture. So um, so there are, besides generation, so specifically for dialogue. So besides generation, there is another problem of retrieval also. So which is also for dialogue, but instead of generating word by word, we rather select from a pool of examples. So, or rather a pool of responses. So instead of generating a next word and generating a whole sentence word by word, you just choose from a huge amount of huge set of response pools. And the advantage here is that many a times word by word generation systems can basically generate anything, in the sense that they are not controlled, because at each time step of word generation, you almost have the whole vocabulary. So it's tough to have a very controlled generation. On the other hand, when you have a retrieval based dialogue system, you have a pool of responses, maybe some 100, 200, 300, and you're just telling the model that, okay, that you need to choose the best response out of them. So we could pose this as a classification problem, or a problem which is maybe understands the context first, that is, by encoding it in some form of a model, like encoding it in terms of an LSTM, or encoding it in terms of a transformer, and then having let's say a softmax or a classification layer to determine which retrieved response is the best. One thing even regarding machine translation, before I move to the next page, if there's since talking about philosophy, the Egyptian Rosetta Stone was kind of the first machine learning system of the world. So basically, it translated that was a system in which you could basically see on a Rosetta Stone, you could see translated fragments, and that was kind of automatically done. So that is basically an inspiration of what further work has been done. Even there was, you see, in 1950s, there was a very famous Georgetown IBM experiment, and that experiment was one of the critical, let's say, critical points of machine translation, because a handful of utterances were automatically translated into another language, and it was for a specific domain, organic chemistry. But the point was that, okay, that resulted in a plethora of work being done further on machine translation. So as far as summarization, machine translation, question generation, and end-to-end dialogue generation go, they pretty much follow paradigm of a sequence to sequence, or a text to text. That is, ingesting a text, coming up with a representation for that ingestion, and then generating a response. Coming down to specific generation systems. Now, all of the above were very generic, in the sense that, just a second, okay, they're very generic, in the sense that they pretty much, like, you could have one system, uh, which is which could work on one domain, and it could easily be translated into another domain. So it was pretty much like work in that was done by a lot of people. uh, so the problem was pretty generic, in the sense that, like, what models could work on summarization or a machine translation or question generation. they pretty much worked on other generation problems as well. So there are other specific generation systems like generating clarifying questions in dialogue for ambiguity resolution. So what this means is like when you have in a dialogue, you sometimes have ambiguities. What whether let's say a bot is conversing with you, and maybe the bot hasn't said something properly, or maybe you haven't said something properly. So how do you resolve that ambiguity? And one side especially of the user specifying an ambiguous request, and there's always the case that when interacting with a bot, users always specify very ambiguous ambiguous requests. And clarifying questions attempt to basically solve that by asking the user, okay, did you mean this, or did you mean this, or did you mean this or this? And that basically user's reply helps to better get his intention forward. So that is what is there's this task of generating clarifying questions. So I would be happy to delve into detail in any one of them. So if any one of you have any questions or any specifics, so my plan is to go with a very broad, like very broadly over all the topics. But if you're very much interested in any of these topics, I'd be happy to even talk about the algo also. But I would just probably go through more breadth rather than depth now, and then maybe if any of you guys are interested, you can just like pause me in the middle and ask a question. So any questions up till now? Okay, so yeah. Mm. So coming down, designing of conversation systems. That is, so conversation systems basically are like more, since they're deployed as a product. They always tend to take the best of all of them and try to experiment. Okay, that what could be a good system which like uses a retrieval also, which uses a generation also, or have individual generators which can be combined and used as uh, and the best answer could be chosen from any one of those. So they're always a combination of multiple systems. So well, some good examples where you guys can look up is basically Amelia. There's IBM Watson also. A lot of open source work is been like very amount of a good amount of open source work is happening in EmoraBot at the Emory University. Then there's Chirpy Cardinal, which Stanford has developed. MilaBot by the Mila University or the Mila School. So there's a lot of work that is happening in developing their own bots, and this always takes in knowledge from different NLP components and tries to merge that or blend that into one system, because conversational AI systems are pretty much a good bench to look at, because you have NLU as well as NLG together, and how you could see even practical problems in a conversation system. That's a good test to basically test any of these models. But definitely there are other there's a lot of NLP happening besides conversational AI also, like embodied AI, etc., which I'll just go through in the next slide. Yeah. So now specifically, what is the state of language today? So where do all language problems stand? So how easy are some problems? Have any problems been solved? Are any problems making progress? So let's see. So named entity recognition and POS tagging. So I so and does anyone want me to go through any of these in detail? I'll try to explain in terms of the inputs and outputs what each of them are, and probably if anyone has any questions, you can stop me right there and ask me a question. Yeah. So some of the most solved tasks pretty much solved to a good level. It's are basically POS tagging. So POS tagging, or the part of speech tagging. So part of speech tagging identifies each word, what part of speech each word is, and that's pretty much 95, 97 plus, and almost 98% in most systems. So you'd always see very close to deterministic performance there. Then there's named entity recognition. So in terms of named entity recognition, it's a um, uh, 7 to 8 common named entities. That's person, organization, location. Identifying those in a sentence is pretty much a solved task, because the width of, or the bandwidth of classification is around 7 to 9 classes. So you have to identify which out of these is a named entity. So Einstein here is a person, UN here is an organization, and Princeton here is a location. So identifying these, at least in terms of 7 to 12 classes, or 7 to 9 classes, is pretty much well above 95%. Uh, but there are other people have started looking at more fine-grained entities, in which they not only represent a word, let's say like by a tag person, but more specific, like it could be a cricketer or a scientist or a professor. And let's say organization can again be a company or a school or a college, etc. So there are these fine-grained named entities also, and then performance there is I wouldn't say that's mostly solved. Then there are tasks which are really making good progress. That's sentiment analysis. Then co-ref resolution. So co-reference resolution is a very interesting task. And there is a harder part of co-reference resolution also. So what co-reference resolution is that, let's say you have a sentence, Carter told Mubarak he shouldn't run again. So what does that he refer to? Does he refer to Mubarak, or he refers to Carter? Right. So identifying that, resolving those references, is basically called co-reference resolution. So the harder part of this co-reference resolution is there's a challenge called the Vinograd schema challenge. So I'll just show you the benchmark. So there's this Vinograd schema challenge, and let's see if we have any examples. Okay, so basically the Vinograd schema challenge has, I'll give you an example verbally. So let's say I was pouring water from the teapot into the cup until it was full. So now that it basically refers to the cup, right? But if I say I was pouring water from the teacup into the cup, from the teapot into the cup until it was empty, that means that it refers to the teapot and not the cup. So if you look at it, if you look at this problem, this is an example of a Vinograd schema. And it's a very interesting example, because how it also tells us that semantics are important for, um, or like meaning of meaning of words around is so important to um, determine meaning further. So like what it means, it is a teapot or it's a cup. So there are interesting problems on that there, and there's a leaderboard there which is called the Vinograd schema, which I think has is not a solved task, and I would say it's a still a really hard task. And as far as co-reference resolution is so concerned, even the best state-of-the-art systems are around 83-84% at the benchmark. Then there's word sense disambiguation. So this is a very fundamental and important problem. So in the question here, I need new batteries for my mouse. So what does mouse represent? Whether it's a keyboard mouse or an animal mouse. So you can determine that from the context, that I need new batteries for my mouse. There's a good chance that that's a keyboard mouse. So that's the task, basically, that identifying the sense of the word. So the word can have multiple senses. So there are others also which handle polysemous words, in which the same word can even like have, yes, like multiple senses. There can be verbs also which could have multiple senses. So then there's parsing, which we talked about, dependency and constituency parsing, and say machine translation and information extraction. For the harder tasks, basically, harder tasks is question answering is a hard task. Now, question answering, there has been immense amount of progress, and there is immense amount of progress left also. So it's one of the very coolest tasks which people want to contribute quickly, because it's even a fun task, and you can see those results, you can see results coming quickly. It's easily understood also from the point of view of let's say sales, because you can even explain this problem very easily to anyone. So question answering receives a lot of attention from everyone, researchers and developers, everyone. So, but still, there's a lot of room for improvement for question answering, as especially uh, in for more of reasoning level tasks, or tasks which reasoning level subtasks, or those which require hopping through multiple answers. So, as an example, what could be a reasoning level question answering task is that you have, let's say, two facts or two sentences that say uh, John travels in a car, or rather John travels in a um, John travels in an X100, and another fact it says that X100, or rather John's car is very heavy. So now we ask a question: is X100 heavy? So answering this question basically requires understanding these two facts not only individually, but uh, combining them and reasoning that, okay, John's car is X100, and we know that John's car is heavy. That means X100 is heavy. So this sort of reasoning, specifically in this example, is like two hops of reasoning. That is, you have taken like two jumps over two facts. So humans are pretty good at doing multiple hops of reasoning, and pretty much see that in a lot of foreign tests like GRE and TOEFL, you'll encounter a lot of reasoning level tasks which are there. So then there's paraphrase generation. So paraphrase generation is also a very important task, because it can help us automatically generate training data also for any task, as well as it could help us say the same thing in different ways. And this task is hard in the sense that when you generate a paraphrase of a sentence, um, you're basically distorting the meaning a bit, but you don't want to distort the meaning too much, because if you distort the meaning too much, it will change meaning. And if you don't distort the meaning at all, you will just have the same sentence. So when you generate a paraphrase, you want models basically that optimize on this really well, that, or else you don't want a model to basically generate the same sentence or generate a sentence which is completely off meaning. And that's why that's one of the reasons why this task is hard. And then there's summarization also, and dialogue, obviously. So dialogue is a very it's among the hardest tasks, because one thing is that dialogue involves not a single pass of reasoning. Since a person speaks multiple times, that means reasoning is also multiple step, in that fashion that you can't, let's say you have, if you compare dialogue with a text classification task. In text classification, you could have a model which basically takes in an input sentence, passes the sentence goes one pass via a machine learning model, and what is basically output is basically your class, whatever class you want. But in dialogue, that's not the case. So you have a context which is there, and you have a new utterance coming, and there's always a new utterance always coming, and you need to update your previous context. So it's not always a one pass thing. So you have to go through multiple steps while doing it, or be able to reason. So reasoning is again a property which is required for dialogue, just as it's required for question answering and paraphrase. So any questions so far? Okay, so can I go further then? I think I've. Okay, so yeah, um, I think I can skip a bit of this because we have less time here. So this was basically what is after 2013, that how NLP changed was we had vector representations of words, and since words could now be represented in terms of vectors, it was easy for uh, computers to consume them. And from word to vec in glove then in 2017 came the transformer architectures, and in between this there was say Elmo, which showed that okay, that instead of having one embedding or one vector for a word, you have uh, you don't keep a map or you don't keep a dictionary, but rather you have a context specific word or a context specific definition. So just as if you go back to the same sentence, so I need new batteries for my mouse. So in this case, mouse will have one embedding, but if you say that the cat was chasing the mouse, in that case, the mouse will have a different embedding or a different vector. And that is a whole, that's the biggest, say, advantage that what came out of these context specific or contextual word vectors called Elmo. And the most revolutionizing thing that NLP faced in the last five years is basically the transform architecture. So the transform architecture is it was unlike, so this was a paradigm shift even in the way modeling language was done, because till now most of language modeling problems were very much inspired from looking at uh, looking at let's say psychological or brain experiments at a very superficial level. It was like okay, we can see that things like attention, like when we read a paper, we probably focus on certain entities, we pay attention to certain entities. So the concept of attention was uh, attention was incorporated into an LSTM. Then LSTM had the individual units of the LSTM, or the individual gates, were very much designed looking at taking a lot of inspiration from some real world phenomena. But in case of transformers, uh, it was just attention. It was just attention. So it was more of, you could assume, like a matrix multiplication, just a matrix multiplication. So it had it could learn basically any sequential structure. So the most famous thing what attention brought was called three types of their attention: self attention, um, encoder to decoder attention, and a masked self attention. So what these attention did was they basically multiplied multiplied a query vector and a key value. So I won't go into that into detail, but with just a large training corpora, the authors of Transformer were able to generate very drastic results in terms of state of the art as compared to 2014 and 2013 with Glove or with Elmo. So, how has language modeling specifically changed from 2016 to 2020? Is that in 2017, okay, you had always had a big machine learning model, and let's say you want to train it for a task. Let's say you want to categorize, let's say emotion, you want to train an emotion classifier or a sentiment classifier. So you needed to train the whole model. So now you either train the whole by LSTM or whole by GRU. So now this is a problem. Now why this is a problem? Because to train models, this was a pretty large model, and you had to collect that much data. So you had to for tasks, for common tasks like sentiment, there's a lot of data, but for tasks which are not so common, like emotion classification, or let's say um, metaphor generation, or even some domain specific tasks which is only catering to the insurance domain or the banking domain, for those you required a lot of hand labeled training data. And all this data was not enough for training a bilistian, because let's say if you want to design a good um, emotion classifier. And the best one till 2017, let's say, was BILE-STM in terms of architectures, unless there was some hidden paper. So the BILE-STM pretty much required maybe 100 to 200 sentences, or at least 100 sentences per label. So if you have 10 labels, you at least required 1,000 to 1,500. And gathering so much data and then labeling them was not that it's not very feasible for every NLP problem. So word to vec and glove was used, and then Elmo came in. So Elmo embeddings were able to differentiate a financial bank from a river bank. So there were two different embeddings for both of them. So if any decision was to be made for any, let's say, a sentence classifier, then information about that, in one case it's a financial bank, in the other case it's a river bank, Elmo embeddings could be utilized. So this had those drawbacks of full training. That is, you had to train all the weights of a model, plus you had to gather a lot of label data. So you had to employ a lot of people, at least one or two people, maybe spend a few days on labeling data, and you couldn't do anything which is outside. So there was always a good chance that you always overfit a model. In 2019, machine learning changed course, and the concept of fine tuning came into picture, and people saw that fine tuning generated really good results. So what that meant was that you take a large amount of corpora of the world, like large amount of text, and you don't need to label that. You just use that as um, for training, let's say, a BILE-STM or even a transformer. And the way you train it is that, if you know language models, the language model's function is basically, given previous words, it has to generate the next word. So if you have a large amount of text, which is basically anywhere on the internet, you could basically feed in any of the first few words and the next word, and that basically effectively becomes your training data. So you do not need to label that. So what people saw is that you could train a very large model using this unlabeled data, so you don't spend a lot of time on labeling it, and then you collect a very small amount of labeled data for your specific task, and that can be sentiment, emotion, or that can be any other domain specific task itself, and fine tune the weights, or basically nudge the weights a little. So you don't train the model from scratch. And this fine tuning is as quick as it can, like from 5 minutes to 1 hour to a day. So that's how quick fine tuning is. So there was basically no need of annotations, and just required a small amount of label data. So that was the biggest paradigm shift from 2017 to 2019. And in 2020, there was another bigger paradigm shift, and this was way bigger. Uh, the concept of few shot learning basically um, had showed really great empirical results in terms of a model called GPT-3. So OpenAI is a collaborative AI research firm, wherein it has investments from, I think, Elon Musk, and I think Microsoft also, and a couple of other people all over, who basically formed OpenAI. They came up with this model, GPT-3. So what they did was they trained a very large language model on basically almost all of the internet. So I wouldn't say all of the internet, but a very large amount of data. And they trained a very large model. So this model was, the size of this model was around 175 billion, and 175 billion was larger than BERT by at least 470 times. So what this means was, as individual researchers, we can't train BERT itself. We can fine tune BERT, but we can't train it from scratch. So, but for GPT-3, it's way tougher now. Now it's such a huge model that no one can, to even have to execute it, like not even train it, but to execute it, have a one-time run or a pass over the model, it takes a few like a few seconds. So that's definitely, if the inference time is slow, then means yeah, the training time is again, that is something very proportional. So the training time will be slower. Plus, I think we are, yes. So I think there's a question. So I'll come to that question next. For that, I'll just finish this off. So this is important because as far as GPT-3, the way GPT-3 was learned was that GPT-3 was able to learn any sequence-to-sequence structure. So it could learn to basically learn how to code in Python, how they should code in JavaScript, how how GPT-3 could basically generate any sequential structure, and that without training data. That's what is basically few shot. Few shot in the sense that few training examples given. So this few meant 1, 2, 3, a handful, an actual handful, unlike how much was needed in task specific fine tuning. So with the help of a few prompts, GPT-3 was just able to generate JavaScript code. So you could just say, okay, generate a JavaScript code to loop uh, from 1 to 10, and you could have a JavaScript code generated from GPT-3. So definitely there are fallacies in that, but there is, in terms of empirical results, this is they have shown really great empirical results. So uh, there are a lot of collaborative efforts that people are working on. There's GEM, which I'm a part of. There's Big Bench also, which Google has uh, started, and even Big Science, which is Hugging Face has started. So I'll move on to the next one. That even so, I've just kept here the handful tasks which are the most like interesting tasks, which besides the ones which you actually get to hear. So if you have time, we can come back. But I think we are already 5 minutes past. So yeah. So this is, I think, yes. So there are some questions in the chat. So yeah. So yeah, so this is basically, so what are the reference books or material to start learning machine learning? So I think a very good start is basically doing online courses, and there's so much content online. Specifically, even my dad also does online courses. So like, I mean, really, so this deeplearning.ai is a very good place to start. It's actually a very nice place to start, in the sense that Andrew NG really covers the topic in real depth and will give you a bigger picture of what things are, and that's more important. And a few like short piece of advice is basically that, okay, enroll in courses like deeplearning.ai, and on a lot of courses on YouTube also, because there are a lot of people who have started their own online lectures, and there are really very good people out there who try to explain some papers, and it's just great to have to look at these 7-minute 5-minute videos and try to understand the gist of the paper. Because even conferences like ACL, EMNLP basically have their 7-minute or 12-minute presentations up there on YouTube, or any other their own conference website. So I think that's a great way to, if you're bored, maybe you don't want to read the whole paper, you can just get a gist of, you can even, I mean, not only a gist, but you can get a good understanding of the paper from the video itself. The other part is to play around with frameworks, specifically Hugging Face and NLP. So Hugging Face is very important now, because Hugging Face, with a very collaborative effort, they've built a um, large code base, and which had made it simpler to train and test NLP models. So I think Hugging Face, definitely people should try out Hugging Face on either a Google Colab or a Jupyter Notebook. So Hugging Face is there. Then Alan NLP, Parlay is a dialogue framework. Spacey is a parsing framework. So it's always good to play around with these, try to test these out, how these outputs, what are the outputs of these. Besides, Kaggle participation is, it's something which I've got a lot of feedback that Kaggle participation helps a lot in terms of, because you have a lot of people already working on some problems, and you try to look at their code and try to improve their code. So it's a nice participative atmosphere. So you should either participate in Kaggle or pick up any leaderboards. So there are lots of leaderboards, which here I couldn't cover. So there are leaderboards for multimodal AI. There are leaderboards for embodied AI, and for basically every NLP problem, every novel NLP problem. So should feel like try to at least get baseline results, or maybe implement the paper and try to get results for each one of uh, like whatever the numbers which are there on the paper. So yeah, and for deeper research, I would suggest everyone to basically be on Twitter. So it's a very, Twitter is actually where most of very good universities and very good conferences are basically will highlight or will um, display their papers, their videos, and there is most of NL, at least for NLP and computer vision, a lot of people are there on Twitter. So there are a lot of discussions happening on Twitter, even though there aren't like, if you don't find a lot of discussions, but there's always a lot of content on Twitter. People share papers on Twitter, and I think that is where you should basically follow all professors, labs, researchers on Twitter itself to get to stay updated. That's the best way to stay updated, to be frank. So yeah, and definitely, like, there are courses, a lot of courses which are there of famous NLP professors, so which are there out there on YouTube. So that is one good way to even go through those, be very much up to date with, uh, and some courses like Chris Manning's course and Juno Choi's course are pretty much they would stand by basically the time. So even if you do a 2019 course now, a lot of the concepts that you learn there will be pretty much applicable for the rest of your life. So I think you should not hesitate to even go back and do some courses which are in 2018, 2019, because especially from the research point of view, you'll find a lot of content is pretty much very applicable across time. And if you're bored, then there are books for light reading to keep yourself motivated. Steven Pinker is a person you could read his books. He talks about the structure of language on his famous book, Language Instinct. And there's one more book called The Stuff of Thought. You could check those also. I'm sorry. Um, yeah, and yes, so that is it. So here are a couple of conferences that I've did. So the good part about most of these conferences now, especially in the virtual format, is that they have released their papers and their videos online. So you could basically look at them and just, so let's say I mean, I could, maybe I want to check out what are the latest Transformers papers. So maybe I see there are a couple of them here. So maybe I'll check AMR to text generation with graph transformer, and you can see you have the whole, basically you'll have the whole pre-recorded video and the slides, and it's just a 7-minute or 12-minute slide. So even if you don't feel like reading a paper someday, you might just go to watch their video quickly. There's a couple of questions here. So how is the industry developing in India, and what is the best Indian university to learn ML? So now, whether the industry is developing really well in India, to be frank, like if it has to be answered in one word, there are a lot of people publishing, and in fact, there's a big trend. The most amount of participants, especially in the world in NLP, are basically from the US, from China, and from India. But India does lag behind the US and China by a lot. US and China are still way ahead. Uh, but India is there's a lot of work happening in India, and especially among Indians, if I would specifically say, there's a lot of work happening all over the world. But anyways, which is the best Indian university to learn ML? So I think if to specifically learn ML, I wouldn't suggest going to a university, in the sense that there's so much content online. that I would suggest um, trying to complete online courses first to learn ML if you want, because there's so much online courses which are available and which are validated by the industry. So like Coursera courses are well known to are very much well known by almost, and it's accepted as a standard. So you should try to do online courses very much, very like it, I mean, take them very seriously, to be frank. Uh, but still, I would not discourage anyone to go through. Like there are a lot of good ML programs which are there. There are some programs which a lot of programs are now offering online MS. And before the pandemic, I would have said that okay, that you would rather go to the university and do an MS. But now the situation has changed, and even though we have vaccine and all, but it's still uh, online will have a good amount of value. Online will definitely have good impact and good value. So there are a couple of universities in the US also, like University of Colorado Boulder, Georgia Tech, even Stanford has a lot of online MS courses. So I think you could and there are Indian MS offerings also. There are a lot of MS offerings from the UK, which are online. So, and they are really very good offerings. So, someone who's wanting to get a degree as far as the namesake, then those are places. But if you want to delve into like research, do more problems, you could rely on online courses and try to focus on getting some publications. I think I've exceeded at least 14 minutes. I'm sorry for exceeding this, and I'm happy that at least like there are a lot of people who have been, and I apologize for taking their lunch time. So yeah, any more questions? Okay, there's a question on what are the salaries levels in this field. I think that's something that's I think uh, it's depends on the it depends on the company. It depends on the work, because the whole NLP space is there is a data scientist also, and the data science is pretty a generic level. So you'll have data scientists, you'll have R&D engineers, and a lot of people do work on NLP. And then there are research scientists also. So every person has a different bracket, and it wouldn't be good to comment on salaries specifically. Any more questions? Uh, okay. Thank you then. Thank you very much. Thank you very much for uh, having me here.